students, good evening. Welcome to another class of Vedantu Karnataka. This is Catherine, your physics master teacher. Quickly, can you let me know if I'm live? Students, good evening. Welcome to. Yes, I am live. Okay. So we quickly wait for our hello monster gang. Hi Anu. So quickly send this link to all your friends. Ask them to join. Hi Ramesh. Yes. Oh, sorry. Yeah, I remember you're Kavya. Yes. Quickly send this link to all your friends. Ask them all to join. Tell them the class has begun. Join fast. Today we're going to learn very important electric potential. Okay. So students on wait. 20. Okay. So students, on Saturday we have an event. Okay. So it's already scheduled on the Vedantu Karnataka channel. You can go to the live and you can see this event. This is our celebration where we celebrate all our achievers. Okay. So all those who got ranks from Vedantu, we are going to celebrate them. So in future we will celebrate you also. Yeah. So please join that session. You will get to know, you will get to hear from all, people who got top scores in NEET, JEE, KCET and all of that. You can get a lot of inspiration. So you can all come join us on Saturday. Okay. You can just go to Vedantu Karnataka live. It's already scheduled. The time, details, everything is there. Yeah. So maybe after a few years, after 2 or 3 years, when you go to IIT, you can meet the same person there. You'll be like, oh, 2 years back on Vedantu live, I saw you. You can build that bond. Yeah. Okay. So let's start. Okay. So let's start our class. So today we are going to discuss electrostatic potential energy. Electric potential energy. This is also part of chapter 1. Okay. So students, those who have not watched the last 2 videos, please do watch them. Okay. So before we look into what electric potential energy is, we will just quickly look at what potential energy is. So you might have learned in your first PU that potential energy is what? Potential energy is the amount of energy stored in a body because of its position, and the formula is mgh. All of you have learned that, right? Yeah, it is the energy due to the position of something. Potential energy is also the capacity of a body to do work. Okay. Potential energy is conservative as well. What does conservative mean? Conservative means if this is a point A, this is a point B, okay? And you can reach AB this way. You can reach AB this way as well. Okay? So you can take path 1, you can take path 2. But whichever path you take, the total work done is going to be the same. It is independent of the path. Okay? So that is a conservative force. The total work done for A to move till B is going to be a constant. It's going to be the same throughout. It's independent of. These are all your first few portion. I'm just brushing it up so that you can understand electric potential very well. Okay. So the work done is the same. Work done along the two paths is the same. It only depends on A and B. It doesn't depend on the path in between. Okay. So potential energy is basically, it can be called as position energy. What does that mean? Potential energy is an energy that depends on the position of a body. Okay. It's called the position energy. Next is the relationship between work done and potential energy. So we have already seen here. So potential energy is the position energy. It also depends on the work done. So whenever you have a conservative force. What is a conservative force? A force that does not depend on the path. It only depends on the initial and final position. However you go from A to B, it's going to be the same. Okay. So for a conservative force, that is like electric force. Electric force is also a conservative force. So for any conservative force like electric force, the work done, okay, the work done is always going to be equal to the negative of the potential energy. Alright. And this is going to be also equal to the negative of the external work done. Okay. Now you might be confused on what is this ma'am saying. Okay. I'll explain it clearly to you. So imagine you throw a ball up. Okay. So when you throw a ball up, what happens? You are moving against gravity. So you are doing some work. You are making the ball move up. Isn't it? Yeah. Gravity is pushing the ball down. But you are trying to go against gravity and you are moving the ball up. So all of the energy that you give to the ball to move up, all of the work that you give is going to be stored in the ball as potential energy. Okay. So I have that here. So here you can see if you do positive work, okay, if you do positive work to move a charge against the field, for example, you are throwing the ball up. Okay, so when you are throwing the ball up, what happens? The ball is going against gravity. So when you are going against gravity, it's going against something. This is the same in electric field. Okay, so in electric field, when you have a charge moving, if the electric field is this way and the charge is moving in the opposite direction, you are going against it. So what happens? All of the work that you do is going to be stored in the charge as potential energy. So the concept here that you need to know, if you're doing work against some conservative force, then all of the work is going to be stored as potential energy. Okay, so potential energy will increase. So what happens? The external force, all the external force that you give to move the body, for example, to lift the block or for a charge to move in an electric field, all the external work that you give is going to be fully stored as potential energy. And that is going to be the negative of the opposite work done. Okay. So the work done of the conservative force. Alright. So let's do a quick question. So this concept gets into your head. Okay. So the question is, a 2-kilogram object is slowly lifted upward by a student through a height of 0.5 meters. Okay. So there is an object. This object is lifted by a student. So initially this object is on the ground and then what happens? This object is lifted by the student and the height by which the object is lifted is 0.5 meters. Okay. Now let us assume that the motion is vertical and gravity acts downwards. Yeah. So you are pushing the ball up, gravity is downwards. So the forces are opposite. So the force you apply is upwards, the conservative force is downwards. So here you can find out the external force that you apply is going to be mgh. So m is 2, gravity is 10, height is 0.5. So you will get 10 joules. So the potential energy stored in the block will also be the same. So whatever work you are doing to lift the block, all that work is going to be stored in the block as potential energy. Okay. Now what about the gravity? How much would the gravity acting on the block be? Gravity is the downward force, the opposite force. So gravity will be in the opposite direction. So that will be minus 10 joules. Do you understand this? So you take a block, you lift it. So when you lift it, you are doing work. So all the work that you are doing is going to be stored as potential energy. So that it means work external and potential energy will have the same value. Now what about the conservative force, which is in the opposite direction? In this case, the conservative force is gravity. If it's an electric field, the conservative force is electric field. So here gravity is downwards, so the conservative force is acting downwards. So that is going to take the value of negative 10. Do you understand? So this relationship is very important. So this relationship is very important when you learn this full chapter. So what is the relationship that you need to know? W external work done on anything is going to be stored as potential energy, and it's going to be equal to negative of the work done on the conservative field, whatever it is. So if it is in gravity, W conservative will be gravity. If it's in an electric field, W conservative will be an electric field. So I want you all to note down this relationship in your books, because we will be using that in the coming questions and the coming concepts. Okay. Now this was a question where the conservative force was gravity. So I just did this question so that you can see what happens. Now we will do a question where the conservative force is electric field, which is what we're going to deal in this chapter. Okay. So let us look at this question. So you have a charge. Okay. The value of this charge is plus 2 coulombs. Okay. So this charge is moving from point A to point B. Okay. So there's a charge that's moving from point A to point B. This is moving against the electric field. Okay. So electric field is going to be in the opposite direction. Charge is moving from A to B. They're in the opposite direction. This is very similar to what we just did. You are taking a block, you are moving it against gravity. So you are moving it up, gravity is down. Okay. So gravity and electric field both are conservative forces. Alright. Yeah. So now let's find out the work done. How much will the work done be? So here the work done will be equal to force into distance. So force will be Q into E times distance, because here it's electric field and charge. So you substitute the values, you will get 1 millijoules. Okay. So all of the work done in moving charge A to charge B is 1 millijoules. Now once it reaches B, all of this work is now going to be stored as potential energy. So what will your potential energy be? 1 millijoules itself. Now what is the conservative work done, which is the work done in the opposite direction? Minus 1 millijoules. Do you understand? So what is the process? You move one charge from one part to another. So when you do that, you do some work. Whatever work is done, that work is all going to be stored as potential energy. Now the opposite direction, there is a work done, because there is a field in the opposite direction. That is going to be the negative of whatever work you do. You understand? Hi Toxic. Hi Subramanya Shubhu. Welcome to the class. Is this concept clear to all of you? If it's clear, can you all put some fire emojis in the chat? Yes, please. Quickly. Yes, my Toxic is back. Toxic, send this video link to all your friends. Tell them all to join the class. So in this chapter, one thing that you need to know is, when you move an object against a conservative force, okay? For example, you take an object, you push it up against gravity. You take a charge, you move it against the direction of electric field. Okay, electric field and gravity both are conservative forces. So whenever you move an object against this conservative force, you are doing work, isn't it? You are doing work to move it. So this work is all going to be stored as potential energy. So this is the key takeaway here. Okay. So whenever you do work against any conservative field like gravity or electric field, whatever work you do, it is going to be stored as potential energy. Okay. Hi Vismita. Hello. Welcome to class. Okay. So in the case of gravity, W is plus mgh. W gravity is minus mgh. Delta U is mgh. Same formula. So W, I'll use the same, this thing, external is what I used here. Let me use the same notation so you don't get confused when you look at the notes. I'll use external itself here. So W external is equal to potential energy. Whatever external force you apply to move the object against the field, it is going to be stored as potential energy. And this is going to be equal to the opposite of the conservative force, which is gravity or electric field. Okay. Hi Nagappa. Hi. Okay. Okay. Next. Yeah, this is in the case of gravity. In the case of electricity, what happens? Same formula. The only difference is to find out the potential work done. For gravity, you use mgh. For electric, you use QED. That's the only difference. Okay. So electric field is in one direction. You're moving the charge in the opposite direction. Okay. So whatever work done you do, it is going to be stored as potential energy. Key takeaway. Is that idea clear? Only then we will be able to move forward. Is that fully clear to all of you? If it's clear to all of you, can you quickly put some fire emojis in the chat? Yes. Quickly put some fire emojis in the chat. Okay. Next, what I'm going to check is I'm going to find out electric potential energy. So what I just discussed was potential energy. So what is potential energy? The amount of external work you do. That is potential energy. Now, what is electric potential energy? Electric potential energy is the electrical energy that is stored. Okay. Same thing. Okay. There's no difference here. It is the same thing. When you take a external charge, you bring it in a direction opposite. It is the work done by the external agent to come back. Okay. So, yeah. My class is best. Thank you. Thank you. Nagappa, if my class is best, please send the link to all your friends and tell them there is a best teacher, learn from her, okay? Because only you, if you all watch the video, will be able to continue the channel and keep giving you best classes. Alright? Yes? So did you all mark your attendance? Did you all like the video? Did you all subscribe? Yeah. Okay. So potential we checked. Now we're going to learn what is electric potential energy. So electric potential energy is when you have potential energy U. Okay, let me draw that first. Imagine you have a charge Q. Okay. And let's say this is a point P. And I have another charge Q which is at infinity. Okay. So it's very far away. So I have a charge Q which is very far away. Now what I'm going to do, I'm going to bring that charge which is very far away. I'm going to bring it very close to this Q. Okay. So the distance between Q and P is R. So after, doing a lot of work, I bring the charge Q till here. Okay. So from infinity, the big capital letter Q is a fixed charge. From infinity, I bring this charge all the way till point P. So I do some work to bring the charge. Yes. So my potential energy, which is U, is basically the work done. Okay. It is basically the work done, which is dW. In bringing a charge from infinity till the point R. So those are my limits. My limits are from infinity till R because my charge was very far away. It was at infinity. I brought it to a point R. Okay. From infinity, I brought it to a point R. So the work done in doing that is dW. Okay. Now what will this be equal to? This will be, okay, this dW is my dW external. Now this is also equal to minus infinity R dW conservative field. Whatever the conservative field is, that one. Same formula, remember, U is equal to dW external is equal to minus dW conserved. So the only thing I'm doing here is I'm applying my limits because I'm bringing a charge all the way from infinity to the point Q. Okay? Nagappa, I'm not very fluent in Kannada, so I'm not able to teach in Kannada. Okay? Swalpa I can talk, but teaching I'm not that fluent. That's why. But don't worry, we have new teachers in the YouTube class. We have 2 more new teachers. They will be teaching in Kannada. Alright. So I will try my best to teach slowly in English. Okay? Yes. Yeah, but all of you, please send this to all your friends and ask them to watch the video because, you know, when I was a student, I didn't have very good lectures because the only thing that we had was we had to listen to our teachers in school. We didn't have YouTube lectures or all anything like that when I was a student. So now, see, if you miss a class, you can go back to YouTube and learn it. That's not you're not losing anything nowadays. So in my days, if we miss a class, we have to sit and figure it out from the textbook. We have to ask our friends and all that. Nowadays, you don't have to do all that. So students, whatever you find, like good channels like our channel, make sure your friends also get to know that there are channels like that. Yeah, right? So if one of your friend benefits from a video, that is going to be a great blessing for you. Okay? So make sure if you find some good content to study, like this channel or whatever good content you study, make sure you send it or share it to all your friends. Okay? That should be your mindset. You should learn to grow together. All of you should bring up your friends and grow together. Yes? And that's really beautiful if you do it that way. Okay? Okay? Yeah. Said that, let's come back. So, let's move on. Now let's look at the mathematical expression for this. As I said, U is the work done, U is the potential, work done, integral infinity to R F dr. So what is force? I will take Coulomb's law. So this in detail I have put it later in the PPT. So from Coulomb's law, you will get this value for potential energy. Okay. Now, if this is Q and the charge that I brought is also Q, right? The distance is R. If both Q and Q are positive, okay, imagine both are positive, then they have to repel, right? Naturally, what happens? They have to repel, okay? So imagine Q is you and small q is a friend that you don't like. So it is very difficult to bring both of you close. It's very easy to make you guys, sit apart. But if I want to make both of you together teammates in a group project, it's going to be very difficult for me because you don't like each other. But as a teacher, I will definitely do that, but still. So so it's very easy for them to repel because they are like charges. But to bring them close, you need to do work on them. Isn't it? Do you understand the concept? Since they're like charges, if you leave them freely, they will just repel. But I want to bring them close. So from infinity, if there's a positive charge here, from infinity, if I have to bring another positive charge, I have to do a lot of work. Which means my delta W is going to be greater than 0 because I have to do a lot of work. So my potential energy will also be greater than 0. Isn't it? Because naturally they wouldn't come together. Now, imagine one is positive and the other is negative. Okay? So if this is positive and this is negative, then I can easily bring Q next to Q. I don't have to do a lot of work. So U can be less than 0. Even if I do very little work, they will still come and attract because they are like two people in love. Right? So even if I'm like, both of you sit on two corners of the class, they will somehow find a way and they will come close together. Right? So unlike charges are like two people in love. They will somehow come close together. So you don't have to do a lot of work to bring them close. So your potential energy can be less than 0 as well. Work can also be less than 0. But if you have two enemies, then you need to do a lot of work to bring them together. So in that case, the potential energy has to be greater than 0. Okay, so that is what is written here. So depending on the charges that are brought together, the amount of potential energy will change. Okay? Nagappa, did you get a good new friend in the chat? Nagappa is Niranjan. Okay. Demise Void finished 12th before a year. Okay. Hi, Demise. Hi, Monster. You joined again. I already told hi to you at the beginning of the class. Okay. So now I will just derive this formula. Okay. U is equal to KQ by R. Here I have not done the derivation. So for PU perspective, for those of you who are preparing for PU, you have to know derivations. So for that, I have the derivation also here. So for the derivation, most important thing is figure. Okay. So at infinity, you have one charge. Okay. And you're trying to bring it close to point P. The distance between P and Q is R. Same figure. I already drew this figure. So initially, the work done is what? Okay, let me do it here. So initially, the work done is from infinity till R. You are applying a force at a distance of dr. So F dr. Okay. So my external force is going to be equal to minus of my conservative force. This we've already learned. Yes. Now what is the formula for conservative force? Coulomb's law. What is Coulomb's law? K. What is K? 1 by 4 pi epsilon. Okay. K is 1 by 4 pi epsilon 0. Okay. So I'm not going to write 1 by 4 pi epsilon 0. I'll just write it as K. K into product of charges divided by square of the distance between them. Famous Coulomb's law. If you don't know, I taught it in the last class. Okay. Coulomb's law states that the force between two charges is proportional to the product of the charges divided by the distance between them. So K Q by R square. Okay. So this is from the last class. Now let's substitute that in our formula for potential energy. Okay. So okay, Niranjan's friend is here. Hi Niranjan's friend. Please subscribe so you can comment on the live chat. Please like the video as well. All of you bring your friends. Only Niranjan has brought his friend. Where are the friends of others? Okay. Now I will substitute that in U. So what is U? Integral infinity to R. Instead of F, I can write minus KQK by R square dr. Now I take all the constants outside. So what remains? Minus K is a constant. The value of a charge is a constant. R square is distance. So what you can do is you can take it outside. Integral dr by R square. Okay. Minus sign will come outside. So the rest of the steps I've not added in this one. But you can just integrate it. What is 1 by R square? So integral of a raised to m is equal to a raised to m plus 1 divided by m plus 1. Okay. So integral of a raised to minus m will be a raised to minus m plus 1 divided by minus m plus 1. This is the same as integral of 1 by a raised to m. Isn't it? So here what will it become? We have integral of 1 by r square. Okay. So this is going to be equal to r raised to minus 2 plus 1, which is minus 1, divided by minus 2 plus 1. This is going to be equal to 1 by r. R raised to minus 1 is 1 by r. Minus 2 plus 1 is minus 1. So minus 1 by r. Yes, those who couldn't see, can you see now? Okay. Yeah. Now, what I will do is I substitute that here. So this is going to be equal to minus K Q K into minus 1 by r minus minus, this will be positive, divided by r. Okay. So that is my potential energy. So for those of you who don't have all the steps, I have all the steps for you. Okay. Yes. Is this clear to all of you? So this is the electric potential due to 2-point charges. So in your PU, you will get a question. Imagine you have 2-point charges. Find the electric force potential energy between them. So you have to consider. You bring a point charge from infinity all the way to a point P at a distance R. Then you have to find out the force. Okay? Yes, no. Can you all put some fire emojis in the chat? What is your name, monster? Please reveal. Okay, let's move on. Now, as I told you earlier, if the two charges are repulsive, which means they are the same, which means they are both positive or both negative, then the value of U should be greater than 0 because you need to do a lot of work to bring them together. Yes? Okay. Now, if the charges are unlike, they will just attract. So, you don't have to do a lot of work. You can be less than 0. So, here the key takeaway is the key takeaway is like charges repel. So, then the work done is going to be negative. Like charges repel, then it's going to be positive. U is greater than 0. It's unstable. Why do I say it's unstable? Why do I say it's unstable? That is because, see, if you have like charges, they repel. Okay? Just I said, you and your friend, the one person you hate in class. You shouldn't have someone like that, but some students have. Okay? So that student and that person you hate in class. Okay? So what happens? You don't like each other. You always move away from each other. And the teacher comes and says, both of you are going to be in the same group project. So what happens? The teacher uses her energy to do work between the two of you and bring you together. It's like you pressing a spring. You compressing a spring. But does the spring like to stay compressed? No. The spring likes to stay free. The moment you leave your hand, the spring becomes free. So it's like a compressed spring, bringing you and your enemy together in a group project. You are unstable. You don't like it. But we, the teachers, we do extra work and we forcefully bring you together. That is when potential energy is greater than 0 and that's why it's unstable. You understand? Now what about unlike charges? They're two people in love. Now they're finding reasons to come close together. So they're happy the way they are. They are stable. Okay? Yes. So when they come together, you don't need to give a lot of energy. So it loses all its energy. That's why the energy becomes negative. Okay. Okay. Next, let's do a question related to the concept that we just studied. Okay. So 2-point charges are placed in vacuum. So I have two charges, Q1 and Q2. They're placed inside vacuum. Okay. So Q1 has a value of plus 3 microcoulomb. Q2 has a value of plus 2 microcoulomb. Alright. They are separated at a distance of 0.5 meters. Find the electrostatic potential energy of the system. Okay. We have to find out the electrostatic potential energy. So now we already know the potential energy of 2-point charges. Those who don't know, that is what we derived here. Electric potential energy between two charges. So we know the formula. So that formula we're going to use here. So what is the formula going to be equal to? U is equal to K Q1 Q2 divided by R. Only R. Why? What happened to the other R? You integrated, it got cancelled. Okay. So K Q1 Q2 by R. What is the value of K? 9 into 10 raised to 9. K is 1 by 4 pi epsilon naught. Into, what is Q1? 3. Micro means minus 6. Into 2 into 10 raised to minus 6. The whole divided by what is the distance? 0.5. Okay. Now if you do the math, you will get the answer. What math should you do? You can multiply all the numbers. So 9 into 3 into 2, 3 2s are 6. 9 into 6, you will get 54. 54 into 10 raised to 9 minus 6 minus 6 minus 6 minus 6. They will just minus 6 should cancel. So you should get, I think there is something wrong with the powers here. What are you all getting? What is your answer? Yeah, quickly let me know in the chat, students, what is your answer? So, yeah, divided by 0.5. So, 9 minus 6. Minus 6 will be 9 minus 6 plus 6. So, that should be 54 into 10 raised to minus 3 divided by 0.5. So, you can do 54 by 5. 0.5 into 10. So, this will just be 10 raised to minus 2. And then you can just divide it. And then whatever answer you get, it will be 108 into 10 raised to minus 3. Okay, you might also get 0.108. This is also possible. Okay. So, see here, okay, this is an application to what we just learned. Look at the two charges. They're both positive, isn't it? So, they are unlike. So, how should the potential energy be? So, both the charges are positive. That means they repel. Which means you had to do a lot of work to bring them close together. Isn't it? Because they are enemies. So you had to do a lot of work to bring them close together. Which means your potential energy should be obviously greater than 0. It cannot be less than 0. If it's less than 0, then these charges won't come together. Only if you do a lot of work, they come together. So potential energy here is greater than 0. So you can see that it's greater than 0. It's 0.1. Okay, so whenever potential energy is, so this can be for your competitive exam, they can ask you when potential energy is greater than 0, then what are the charges? So if the potential energy is greater than 0, the charges are always positive, positive or negative, negative. Basically, they're the same. They're like charges and they repel. Okay, now there's one more question. So here you will see what happens when two unlike charges come together. So here the first charge is plus 5, the second charge is minus 5. And okay, here they are at a different distance also. All right. So they are at a distance. If this is 0, this is 10 centimeter. This is minus 10 centimeter. Okay. So the distance is 10 centimeters and minus 10 centimeters. So let's do that. So I'll use a different color. So formula is U is equal to K Q1 Q2 by R. Okay. Now, what is the total distance? 10, 10. Sign you can ignore. It will be 20. So, this will be 9 into 10 raised to 9 into 5 into 10 raised to minus 6 into 5 into 10 raised to minus 6. The whole divided by 20, which is 0.2. 0.2 meters. Okay. So, 5 into 5 is 25. 25 into 9 will be 225. So, this will be 225 into 10 raised to minus 3, the whole divided by 0.2. So 225 by 2, 225 by 2 if you do, you will get 1125. Okay. So the answer will be 1125 into 10 raised to minus 3 joules, which is 1.125 joules. Okay. Now, there was a negative sign here. Yes. So, it was negative 5. So, this will be negative. So, you can see the answer is going to be negative. Okay. Because your charge is, one charge is negative. The radius is also negative. So, here you have negative 5. Okay. So, if you put the negative sign, your final answer will also be negative. Why is it negative? Because they're like charges. They're two lovers. They're unlike charges. They're two lovers. They like to stay with each other. So you don't have to put a lot of energy. Okay. So these are two examples. See, I am giving you theory problem. I mean a theory part, and then I'm giving you different problems so you understand what I'm trying to do. Okay. Students, this is something that I took a lot of effort to do. So I would appreciate if you can share it to all your friends and, let them also, make this helpful. Like let this be helpful to them as well. Yeah. Okay. So those are the two problems. Now imagine you have a system of charges. This is for two charges. We found out a method to use potential energy for two charges. Now imagine you have 10 charges. 1, 2, 3, 4. I don't want to draw 10. So let's say you have 5 charges. Okay. Now they will all have a potential energy between them, isn't it? Won't they all have a potential energy between them? Uh, okay. 1 second, students. Students here, sometimes they might ask you for the graph as well. Okay. So the graph of potential energy and distance. So let's say you have R here, you have potential energy here. Okay. So initially, if the charge is repulsive, if they're repulsive, which means they're enemies, potential energy is always greater than zero. So it will be like this if it's repulsive. Now, if the charges like each other, which means they are lovers, then what will happen? The potential energy will be like this. It will be attractive. Okay? Do you understand that? Yes. Okay. Now, the next thing that we're going to move on, we're going to look at is electrostatic potential energy of a system of charges. As I said, if you have so many charges. Now, if you have two or more charges, okay, the total potential energy is of the system is going to be the sum of the potential energy of each pair. So, let's say you have 1, 2, 3, 4 charges. Okay. So these two will have a potential energy. These two will have a potential energy. These two will have another potential energy. These two will have another potential energy. There will be potential energy between these two and these two. These are all the possible combinations. So if you add the potential energy of all these, you will get the total potential energy. Okay. Let's consider another figure. Let's say you have a triangle. You have three charges. Okay. Because of this, yeah. So now if you find out the individual potential energies linking all of them, you get the total potential energy. Let's say I have one more charge here. Then this. Okay. So they have to be, you have to find out the individual potential energy between all the two pairs. All two charges you take, you find the potential energy between them. You do it for everything. You add them all, you get the total potential energy. Okay. So the total potential energy of a system is the sum of potential energy between every pair. What do you mean by every pair? Between every two charges. Alright? See, it's just like a group. Imagine a group has 10 people. The relationship between each two of them determines the whole vibe of the group, right? Only if all the 10 people like each other, then the vibe will be good. But imagine two people don't like each other. That will contribute to a negative effect. So each two people, the vibe between them determines the vibe of the whole group. Okay? See, right now, even in the chat, you got so many new friends. Depending on how many friends you have, you're more interested, right? Yeah. Okay? Yeah. So, yeah, that is due to so many charges. Now, let's do a question. Three identical points. Okay. So, three identical point charges of charge Q is 10 coulomb. They are placed at the corners of an equilateral triangle. Okay. So, there's an equilateral triangle. This is Q1, Q2, Q3. Okay. They all have the value of 10 microcoulombs. Okay. Now, each side, okay, let's say it is placed at each part and each side is A, okay, and A has a value of 0.2 meters. We have to find out the total electrostatic potential energy. So let's first write down the formula for potential energy. What is the formula for potential energy? KQ square by R. That is the formula for potential energy. So this is going to be equal to, what is the value of K? 9 into 10 raised to 9 into Q is what? 10 into 10 raised to minus 6 square. Why am I taking square? Because the charges are all the same. And R is 0.2. If I do the math, what will I get? 9 into 10 raised to 9 times 100 into 10 raised to minus 12, the whole by 0.2. So 9 by 2 is going to be 4.5, and the powers, they will all cancel. 9, 10, 11 minus 12, 0.2. They will all cancel. So here I multiply it with 10 and 10. Okay. So all the powers total will cancel. 9 by 2 will be 0.5, 4.5. So you will get 4.5 joules. So what is 4.5 joules? 4.5 joules is the potential energy between two charges. Like it could be between Q1 and Q2, or Q2 and Q3, or Q3 and Q1. Okay. The potential energy between one set is 4.5. So the potential energy between these two is 4.5. Between these two is 4.5. Between these two is also 4.5. So the total potential energy is 4.5 into 3, which is 13.5. So the potential energy of the whole system is 13.5 joules. Do you understand that? Yes? Okay. How did I get that? I found out the potential energy between two. And because it's all the same, I'm just adding it up or multiplying. Okay. Now, is this clear to all of you? Next is the change in potential energy of a system of charges. Okay. So let's say there is a system. Okay. It has 1, 2, 3, 4, 5 charges. All right. Now what happens is this gets rearranged. Okay. So the same system now has, the position of the charges have changed. Okay. So let's say this becomes here, and then this goes here, here, and here. Okay. So we have a system of charges, and now it is rearranged to another system of charges. So for this rearrangement, to rearrange, I had to do work. The charges won't go and move by themselves, right? I had to do some work to make the system from A to A dash. To rearrange the number of charges or the order of charges, I had to do some work. Yes. And that work is going to be equal to what? The external work that I do. And all that work is going to be stored as the potential energy in that full set. And that potential energy is going to be equal to the final potential energy minus initial potential energy. Okay. Why can I do that? Because this is something that we already learned. Okay. Electric force is conservative. So whatever work you do, all that work gets stored as potential energy, and the change in potential energy will be what? Initial potential energy minus final. So the only difference from this to the previous is there we had only one potential energy because it's one system. So here there is first system, it's rearranged into another system. So potential energy is changing. So the change in potential energy is U final minus U initial. That's all, the only difference. Okay. Do you understand that? Do you understand that? Hello, Sunita. Hello, Praveen. Okay? Okay. Now let's look at a question. So, four identical charges. 1, 2, 3, 4. 4 identical charges are placed on the sides of a square with lengths 1 meters, 1 meters, 1 meters and 1 meter. Okay. Now, all the charges are the same. So you tell me, will they be attractive or repulsive? They are all 2 microcoulombs. They are all the same. Okay. Now, what happens? This square becomes a bigger square. So the same square will now become a bigger square with sides 3 meters. Okay. So what happens to the what is the change in potential energy? What is the work done? Is what we have to find out. So first, let's find out the potential energy between two, like we always do. Okay. So okay. So this is the figure. So let's find out the work done between two first. So there are 4 sets. So let's say we're taking Q1 and Q2. Okay. So the potential energy is going to be equal to K, Q1 and Q2. So Q square divided by the distance between them is B. So this into 4 is going to give me the total potential energy, isn't it? Because I have to find out the individual potential energy between one side, second side, third side and fourth side. So let's do the substitute with values. So this is going to be equal to, okay, not just that, something that something that we have ignored actually. So here, these two and these two will also have a potential energy between them. You understand that? So the charges will have potential energy between them in however possible. So in this case, they will all have potential energies. These two will have, these two will have, these two will have, these two will have. The diagonal ones will also have a potential energy. Okay. So this is the potential energy because of sides. Now this one plus the potential energy because of diagonals. How do I get that? There are 2 diagonals. So how much would this side be? This side will be using Pythagoras theorem. 1 square plus 1 square is going to be equal to square root of 2. So see, hypotenuse square is equal to side square plus side square. So hypotenuse square is going to be equal to 2. 1 square is 1, 2. So hypotenuse is going to be equal to square root of 2. Okay. So I'm doing all the basic steps so that all of you understand. So hypotenuse is going to be square root of 2. So here the distance between the 2 charges is going to be square root of 2. There are 2 diagonals. So 2 into KQ square by root 2 into B. B is just 1. Okay. Root 2 into B. B is the distance between them. Okay. So here I'm just putting B because, in the next, I'm just trying to write a general formula. Alright. Okay. So now what I do is I just substitute the values. So what is common here? KQ square by B is common. So KQ square by B comes out. So what remains? 4 plus 2 divided by root 2. So this is what? 2 divided by root 2 will be root 2. 4 plus root 2. Now I can substitute the values. What is K? 9 into 10 raised to 9 into what is Q? 2 into microcoulomb. So 2 into 10 raised to minus 6 square. KQ square. B is 1. So you can ignore it. Times 4 plus root 2 is 1.414. So if you just solve it, you will get 0.195 joules. Okay. So 0.195 joules is the total energy of the cube. Now what happens when the sides become 3B? So it's very easy. You just have to substitute 3 here. Okay. Same steps, but the only difference is U will be KQ square divided by 3B into 4. Okay? Plus 2 into KQ square by square root 2 into 3B. So you take 3B outside and then you solve it. That's the only difference. Okay? So instead of B, it becomes 3B. Alright? So now you have the initial potential energy of the cube. You have the final potential energy of the cube when the cube became big. So if you subtract the two, okay? If you subtract U final minus U initial, if you subtract the two, you will get the total potential energy. And you can see that the value is negative. The value is negative. Why is the value negative? Because they are the same charges. They're repelling. See, it's just like, four enemies staying close together. And then what the teacher comes and says, it's okay. Now you can move away. They will be very happy to move away because they're enemies, isn't it? So when the cube becomes big, they'll be happy to become big. So that is why it's negative. Whenever they're happy, the value is negative because you don't have to put any value. They will have their own value, so it's negative. Okay? So I want that idea to get into your head. Whenever it's repulsive, potential energy will be negative. It will be less than 0. Okay? Now, if you want to find out the work done by the conservative force, it will be the negative of this. It will be positive. Why? Because work done externally is equal to minus delta. Is equal to plus delta U. This is equal to minus delta conservative force. Okay? So, if delta U is minus, then conservative force will be plus. Alright? So, when the size is increased, charges are so happy. That is what the negative sign indicates. Okay. I am good, Praveen. I hope you are good too. But I am a little sad because none of the students have joined class. So, can you all show me some love by sending it to all of your friends and asking them to join? Because it takes a lot of effort to make content and take these classes, right? Okay. Next, we are going to look at electric potential. So, till now we looked at potential energy. Okay, you have to understand the difference. Till now we looked at potential energy. Now we are going to look at electric potential. They are two different things. Okay, what is the difference between the two? Potential energy is W. This W by Q is electric potential or voltage. You understand? Okay. So potential energy was what? U was delta W. Work done was potential energy. They are the same. Now the amount of work done per unit charge is potential. Okay. So difference between electric potential energy and electric potential is that electric potential energy divided by Q or work done by Q is electric potential, which is also called as voltage. So what is voltage or electric potential? It is the amount of charge, it is the amount of work used, it is the amount of work that is done by a charge to be brought from infinity to a place inside the field divided by the amount of charge. Do you understand? So mathematically you can write this as, this is equal to 1 by Q, I can take it outside. From infinity to a point P, work done is what? Force into displacement. So FDR. I can do this as well. It is a scalar quantity. It does not depend on any direction. It only depends on the value of the charge. And the unit, SI unit is volt or joule per coulomb. Okay. Now we'll learn more on electric potential. So this is what the difference is. This is just a summary table for all of you. So this is the energy per unit charge. This is the total energy that the charge has. Voltage is energy by charge. Okay. Okay. Now there's a quick question. So if the potential at a point is 5 volts. Okay. So let's say the potential is 5 volts. And you place a plus 2 microcoulomb charge. Okay. So you have a plus 2 microcoulomb charge. What is the potential energy? Very easy. Potential energy is what? No, let me write it in a way you understand. So voltage is what? Voltage is same as potential energy but divided by charge. Isn't it? Potential energy and work done is the same. So voltage. So now V is electric potential, U is electric potential energy. Okay. So electric potential is equal to electric potential energy by Q. So from this you will get U is equal to Q into V. And you just do it. So U is equal to how much is Q? Plus 2 microcoulomb. So 2 into 10 raised to minus 6 into voltage, which is 5. So this is 5 into 2, 10. 10 into 10 raised to minus 6. 10 microjoules. Voltage is 5. Okay? Do you understand this? Yes? No? Can I have some response, students? Yes? See, imagine you think about me. I am just sitting in a room, I'm talking to a screen and I'm teaching, and I don't see your responses in my chat box. So, what should I do? Just sit and cry. But it's okay. At least students watch the recorded version. I feel like students want, your attention span is so low that you want to watch the video faster, so you watch it recorded, right? So all those who are watching it recorded, please let me know in the comments how the class is, okay? So I know. None of my live chat students are that active. They're not telling me how the class is, okay? So all the students who are watching it recorded and watching it on 2x speed or 1.5, please let me know in the comments on how the class is, okay? Because I really expect feedback from you. Okay. Sunita is listening to my class. Lakshman Power is also listening. Okay. So, yeah, that is what we were discussing. We were discussing about electric potential. Now, see, we talked about potential energy. We talked about potential energy difference. Potential energy is U. Potential energy difference is delta U, which is U final minus U initial. Similarly, we're going to talk about electric potential, which is voltage, and potential difference. Same thing. So delta V. Earlier what we discussed was delta U. So what is delta V going to be equal to? VB minus VA. Okay. So this is going to be equal to what? We already know it is work done by Q. So this is going to be equal to, again, I take Q outside, 1 by Q, from A to B, F into dr. Okay. So work done will be Q delta V. So think of electric potential like a hill, okay? You are moving a ball from the top to the bottom. Okay, so the difference in height gives you the energy of the ball. That's all. The electric potential difference between 2 points, it just tells you how much energy is lost or gained. Okay. Now, yeah, a battery provides, this is just an example here. A battery provides 1.5 volts between its terminals. What does that mean? If it has two terminals, it gets 1.5 volts. What does it mean? It means 1 coulomb of charge from the negative to positive terminal gives 1.5 joules of energy. That's what potential difference means. Okay. Okay. So let's look at a question for potential difference. A charge of Q2 microcoulomb is moved from point A, where the potential is VA, which is 10 volts, to a point B, where the potential is VB, which is 4 volts. Find the change in electric potential energy of the system. So now I have to use my new formula. So what is the formula? Change in voltage is change in potential energy divided by Q. Yeah, that's the difference. So now change in potential energy is what I have to find. So that will be Q into delta V, which is QVB minus VA. So I just substitute the values. What is Q? 2 microcoulomb. 2 into what is VB? 4 volts minus 10 volts. Minus 10 volts. And this is 2 microcoulomb. So 2 into 10 raised to minus 6. So this is 2 into 10 raised to minus 6 into minus 6. So del U is minus 12 microjoules. Okay. 4 minus 10. Yes. This is the potential energy. Okay, now let's do one more question so that this concept becomes, stored in your head. In a system of charges, the electric field does 10 joules of work. Okay, so electric field is doing 10 joules of work in moving a charge of 2 coulombs from point A to point B. So this is point A, this is point B. 10 joules of work is done to move a charge from point A to B. Okay, so potential energy is what? The work done. The work done. So this is minus 10 joules. Okay, minus 10 joules. So potential energy difference will be del V will be del U by Q, which is minus 10 by 2, which is minus 5 volts. Now, why did I take minus 10 joules? Because the electric field is doing this work. So that's where conceptual clarity is important. See, the external field, that external work that I do to move my charge from A to B is stored as potential energy. Okay, so whatever work I do externally is going to be stored as potential energy. These are both going to be positive. This is going to be equal to the negative of the work done on the field. Here 10 joules is the work done on the field. So if 10 joules is positive, then potential energy should be negative. You understand the concept here? Yes? So if I have to move a charge from point A to point B, I apply an external force. Okay? So the work I do to bring point A charge to point B is stored as potential energy at B. I am doing some work. I am pushing the charge all the way till B. At B, it is going to be stored as potential energy. So the amount of work I do and the amount of potential energy is going to be same. But electric field is in this direction, it's in the opposite direction. The work done in the electric field direction is going to be negative of the potential energy and the external work. Okay? Yes. Okay. One more question. Let's look at one more question. An electron is moved from a point where the electric potential is 20 to minus 20. Okay, so this is V1, V2 plus 20 to minus 20. An electron is moved from plus 20 to minus 20. Okay, so electrons, particles always move from higher potential to lower potential. So the question is, find the change in electric potential energy. Okay, electric potential energy, students, please don't get confused. Electric potential energy is U. Electric potential is V. Okay, so this is what? Q into del V, which is Q into V2 minus V1. What is the value of Q? It is an electron. So it's obviously 1.6 into 10 raised to minus 19. It's an electron, so it's negative, into V2 minus V1. V2 is what? Minus 20. V1 is 20, but then you have to subtract them. So this will become minus 1.6 into 10 raised to minus 19 into minus 40. So this will be 6.4 into 10 raised to minus 18. Negative, negative, it becomes positive. Okay, so the work done is positive. Obviously, the work done should be positive. Why? Because these are two unlike charges. They are like lovers. They like to stay together. Okay, I hope you're understanding the concepts here, because that is the most important part. Okay? Yes, Praveen, very good. Now, You also have to find out the work done by the external force. Work done by external force is always same as potential energy because the potential energy is from work done by external force. So W external will be the same value plus 6.4. Now if the question was find out the work done by the field as well. Work done by field, by conservative field will be minus 6.4 into 10 raised to minus 18 joules. Okay? Yes? Yes. Okay, one more question. Particle of charge Q is equal to 1.6 into 10 raised to minus 19. Okay? And it is accelerated through a potential difference of V is equal to 6.4 kilovolt and which is equal to 64,000 volts. The mass M is 1.67 into 10 raised to minus 27 kilogram. We have to find out the kinetic energy gained and the speed of the particle. Okay, that's something different, right? Okay, let's do it. So there is a potential, a particle is moving through the potential. Okay, so one thing that you need to know here is, students, whenever you have a potential, okay, so whenever you have a potential, here you are doing work, it's going till here. Once you reach here, it is stored as potential energy. But initially, since the particle is moving, won't it be kinetic energy? So, potential energy U is equal to Q into V. So, this potential energy lost is going to be the same as the kinetic energy gained, isn't it? So, energy is conserved. That is one law you learned in your first PU. So, imagine work is done and all of it is stored as potential energy. Okay. Now, the moment when it's moving, when there's no potential energy, it should have energy. So, the energy should be obviously kinetic energy. So, kinetic energy gained is equal to potential energy lost. So, it should have the same value, which is QB. So, you can just use the same thing. So, Q is 1.6 into 10 raised to minus 19 into voltage, which is 6400, which is 1.024 into 10 raised to minus 25 joules. Now, the next, sorry. Yeah. Now, the next part is to find out the speed. How will you find out the speed? We already know kinetic energy is what? Half mv square. So you can equate it. Half mv square will be 1.024 into 10 raised to minus 15. So from this, half mv square is equal to ke. So v square will be ke into 2 by m. The whole square root will be v. So you substitute the values, you should get the answer. Okay. So what will it be? Let's say it's going to be 2 into kinetic energy we already got. 1.024 into 10 raised to minus 15, the whole divided by. Mass is 1.67 into 10 raised to minus 27, square root of it. Okay. Square root of it. So let's do the math. So you can write it as 2 into 1024 by 167 and then you can find out the square root. Okay. And then you should get 1.107 into 10 raised to 6 meters per second. Okay. So you have the kinetic energy and the speed. Alright. Next is electric field due to a point charge. I had to do some. Okay. Yeah, electric field due to a point charge. I'm going to do the derivation for electric field due to a point charge. Sorry, Electric potential due to a point charge. Okay. Electric potential energy between two charges we did. Now this is electric potential due to a point charge. Okay. So let's consider point charge Q. Okay. So if you have a point charge Q, the potential on that point charge is what? The work done divided by the charge Q. You take it as small letter. Okay. Charge Q. This work done is always the external work that you are doing. Okay. And this is always going to be stored as potential energy. So W and U is the same. This means that work done by an external agent on one unit positive charge in bringing a test charge Q from infinity to a distance r without acceleration will be equal to the Coulomb's law. Okay. So imagine you have a charge here. Okay. At a distance r from a point charge Q. Let's make the figure. Okay. So you have a point charge Q. You have another charge Q coming from infinity. Okay. So the force by which you bring it is equal to the Coulomb's law, which is QQ by R square. Coulomb's law has R square. Okay. Now, the amount of external work that you do to bring that charge close is equal to the amount of work will be dW external. The amount of external work is going to be equal to force into displacement, the distance between the charges, which is KQQ by R square times dr. And then you take all the terms, constant terms inside. So, and then you can just have to integrate. Okay. Integration, it's written here, but I'll just write it once again for you. So, dW external is going to be equal to K. I'm not writing 1 by 4 pi epsilon naught. Okay. You have to understand 1 by 4 pi epsilon naught is always the same as K. Okay. Yeah. So, K QQ by R square dr. Now what I will do, I will integrate. What is the highest limit? The highest it can go is till infinity. What is the least it can come? It can come all the way till R. So this is dW is equal to K is a constant, Q is a constant, Q is a constant. So integral infinity to R dr by R square. So integral of dW is obviously going to be W. This is going to be equal to KQQ. What is integral of 1 by R square? I've already done this once in the previous derivation in this class itself. So it's going to be equal to 1 minus 1 by R. Okay. So this will be minus 1 by R into R and infinity. Okay. Now we have W. So W is equal to KQK by R. KQK by R. To find out voltage is W by Q. So this will be KQ by R. Okay. You can ignore the negative sign because it is a scalar quantity. So you will get V is equal to KQ by R. Oh, Azrush, I remember you. Azrush is one student who attends all my classes. Okay, Azrush watched from the beginning. RXBTCC, it did hurt. What hurts me is that you're not listening to my class. Okay? Yeah. Who else is listening from the beginning? Please let me know. I'll be very happy. So, is this clear to all of you? Please ask me some doubts so I can explain it to you. Okay? So, this is the electric potential due to a point charge. Now, electric potential due to a system of charges. Imagine you have a system of so many charges. Okay? So So if you have a system of so many charges, let's say this is a point. I have a charge here Q1. I have another charge Q2. I have another charge Q3. I have another charge Q4. Okay. So if you have so many charges, if you have a system of charges, then the net potential, let's say this is the point P where I need to find out the net potential. Okay. So the net potential at P will be equal to the sum of potentials due to, I don't look at the sign because this is a scalar, so I will write it as scalar. Scalar sum of potentials due to all the charges. Due to all the charges. And this is similar to superpositioning principle. Okay. So Vp, which is the total potential at point P, is going to be equal to V1 plus V2 plus V3 plus how many ever are there up to Vn. So this is also going to be equal to what is V? V is KQ by R. KQ1 plus KQ2 by R2 plus KQ3 by R3, and then it just goes on like that. So in total, V is going to be equal to sigma Ni is equal to 1 to N KQ by R. Okay? Okay? Yes. So total electric potential is going to be the scalar sum of potentials of each of the individual charges added together. Let's look at a question so that concept is also clear to you. Okay? Yes. So charges plus Q and minus Q are placed at the vertices B and C of an isosceles triangle. Okay? Let's draw a triangle. So many triangle questions, no? So this is A, this is B, this is C. So you have two charges plus Q and minus Q placed at B and C. It's given to you in the question. Find the electric potential at vertex A. Okay. And the distance is R. AB and AC both are R. Alright. So let's do that. So potential at A will be equal to the potential at VB. The potential at A should be equal to, I'll draw that 1 second. I'll use yellow. Okay. So potential at A should be equal to the potential of B with respect to A and the potential of C with respect to A. Okay. So potential of B with respect to A will be how much? K. B is plus Q divided by R. Plus, what is the potential of, this is C, okay? Erase, come on. My erase, okay, this was the eraser, I'm sorry. VC, okay. Plus, what is the potential of C with respect to A? K minus Q by R. Now, when you do the math, this is what? Plus KQ by R minus KQ by R, it's going to be 0. Isn't it? It's going to be 0. So the potential at point A because of point B and C is what? The potential at B with respect to A and the potential at C with respect to A. So this is what? This is where this is applied. Okay. Electric potential due to a system of charges. Its application is this question. Okay. So every time we do a concept, I'm giving you a question so you understand where to apply it. Alright. Okay, now coming to the last topic of the day, equipotential surfaces. Okay, this is the last topic for the day. So all those who are thinking, all those who are tired, don't worry. I'm just going to finish off. This is the last topic for the day. Alright, equipotential surfaces. So we looked at what is potential energy. We looked at what is electric potential or voltage. Now we are going to look at equipotential surfaces. So first thing you need to know, students, is that equipotential surface is an imaginary surface. Okay, it's not really there. It's just an imaginary surface where the electric potential is same at every point. Okay, so for example, imagine I have a charge plus Q and I have field lines coming out like this. Okay, imagine if I draw a circle like this, the field line at every point on the circle is the same. Okay, now along this circle, the potential at every point on the circle is the same. Okay, so it is an imaginary surface where electric potential is the same at every point. So in this figure, you can see the potential here, 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 here. You know, the potential here everywhere is going to be the same. Now, look at the next circle. Here also the potential here, the potential at A and the potential at B and the potential at D and the potential at F will all be the same. Okay, so an equipotential surface is an imaginary surface where the potential is the same throughout. So you might be wondering, ma'am, whenever there is a point charge, so the potential will always be a circle? Yes. For point charges, the equipotential surface will always be a circle. Okay. All right. So, yeah. In case of a point charge, the equipotential surfaces are always circles or spheres. Now, imagine there is a uniform field. Okay, not a point charge, but a uniform field. See? Now, there are 5 field lines coming. How do I make a surface such that the potential is the same? I have to keep a parallel plate. Okay, so let's say this is parallel. So, field lines are coming in. Okay, can you see that? My video is a little slow here. So only after I show you something, I can see if it actually was shown on my phone. Okay. So yeah, let me show you this. So if this is a surface, okay, this is my equipotential surface. You have, okay, I don't know my equipotential surface. You have 10 field lines coming. I don't have 10 hands. So you have 10 field lines coming. Okay. 10 field lines coming. I need a surface such that all the 10 field lines, wherever I have the same potential on all the 10 field lines, I need a surface there. So I can't put a sphere. So I put a parallel plate. So the lines crossing the plate will all have the same voltage. That is where the surface will be. The next point where all the lines are going to be the same, that is where the next surface is going to be. So for point charge, equipotential surfaces are always spheres. For parallel charges or electric fields, equipotential surfaces are always parallel plates. It's always perpendicular. That is also another rule. Always perpendicular to the field lines. So if the field line is like this, equipotential surface is like this, perpendicular. You can see in all the cases. See here. Here, see, this is perpendicular, this is perpendicular, this is perpendicular. So if this is the sphere and this is the field line, it's always perpendicular. Okay, so the equipotential surface and the charges should always be perpendicular to each other. That is the next rule. Then, for a uniform field, the equipotential surfaces are parallel planes. Work done in moving a charge along an equipotential surface is zero. What does that mean? See, if I have a charge, or if I have a charge here, I have another charge here. If they're like charges, they'll easily come close. If they're unlike charges, I need to apply a lot of work to bring them together. But in an equipotential surface, they will easily come together. I don't have to do any work. Why? Because it's the same potential everywhere. See, it's like when you are in your room alone. You just roam around the room like you're a free bird. There's nothing to prove to anybody. You just roam around, you have fun. That's how an equipotential surface is. Throughout the surface, the voltage is the same. Nothing changes. The voltage is the same. Everything is same. So there is no need of any work done. So the work done in an equipotential surface is zero. Okay? Yes? Thank you, Azrush. You're the best teacher, beauty with brains. I haven't seen you, Azrush. I would have given you the same compliment. Okay, I believe you are also a beauty with brain. I mean, I don't believe you are. Now, who decides beauty standards? This is 2025. Every person is beautiful. Okay, so that is equipotential surface. Now let's do a question on equipotential surface. A positive charge Q, which is 2 microcoulomb, moves along an equipotential surface in an electric field. How much work is done? Simple question. I don't even have to do anything. See, if a charge moves on an equipotential surface, then the work done is 0. Okay. Why? Okay, mathematically, why does that happen? Because U is equal to Q delta V, that we know. So delta U is the same as work done. So work done is also Q delta V. In an equipotential surface, the voltage is same throughout. So this is Q into 0, which is 0. Potential is the same throughout. So answer is 0 joules. Okay. What is happening between Uday Gowda and Sunita? Okay. Next is the equipotential surface for a system of two identical positive spheres. So imagine you have a positive Q here, another plus Q here. Okay. So field lines are like this for positive charges. They're always moving out. Okay. But here they don't come close together because they repel. So equipotential surfaces, what is this? Okay. So equipotential surfaces will be spheres. So it will be, here there will be a sphere. Here also there will be a sphere. Okay, I'll show it to here. Why do you have to see my pathetic drawing? So you can see the surface will be formed only where the potential is the same. So here there is a sphere. Here there is a sphere. But here there cannot be a sphere because there are no field lines here. So that cannot be an equipotential surface. Even in this case, this cannot be an equipotential surface. Why? Along this part, there are no field lines. So there is no potential. So there the potential is different compared to the rest. So where is the next equipotential surface that can be drawn? It can be drawn like this. So along this arc, the potential is the same. Okay. So equipotential surface is not always sphere. It is just a shape such that the potential is going to be the same everywhere. So here it cannot be a sphere, isn't it? Because along this part, there is no voltage, there is no field lines. So that is not an equipotential surface. So there is no circle there. Do you understand that? So this is the equipotential surface. Now, last relationship. This is the relationship between electric field and potential. So what is, see, electric field tells you how quickly electric potential changes with distance. So imagine you have field lines like this. Okay. Field lines like this. So here, if you have very close equipotential surface and here you have very far away equipotential surface, what does that mean? If the equipotential surfaces are very close together, that means the electric field is not changing a lot there, which means the voltage is the same throughout. So you can have lots of equipotential surfaces. Do you understand that? If the equipotential surfaces are very close together, that means the change in electric field is not that much. The voltage is the same everywhere. But if you can only draw, like if you have this much distance and if you can only draw two equipotential surface, which means voltage is drastically changing. It's not being the same anywhere. That's why you are not able to draw the equipotential surface. So that change is called potential gradient. Okay. So E is equal to minus dV by dx is the electric field. It tells you how fast the potential changes with respect to distance. Okay. And potential always changes from higher, electric field always flows from higher potential to lower potential. That is what the negative sign represents. Okay. So what is potential gradient? So as you move along an electric field, it tells you how potential changes with distance. And how do you know that? By looking at the equipotential surfaces. If you have like three surfaces, then you have one after a long distance, it means the potential has changed drastically, which means the potential gradient is high. Okay. Do you understand that? Yes, no. So now there is a relationship between field and potential. Okay. So the relationship between field and potential. How do you do that? So one thing that we know that the field, the work done in the external field, okay, field or conservative field or electric field is what? Minus du. This is equal to positive work done externally, but with respect to the field, it's minus du. What is work done? Work done is force into distance moved, and this is equal to minus du. Now what I will do is I will divide both the sides by q. Okay, I will divide both the sides by q. Now what is FDR by q? I mean F by q. F by q is electric field. So this becomes E into dr. And what is du by q? It is potential voltage. So this becomes minus dV. Now from here E will be minus dV by dr. Students, this is a very easy derivation. So you might have, the question could be, show that this could be the question. Show that electric field is the negative gradient of electric potential. Sometimes the question for your PU exam is also like this. Electric field is a negative gradient for electric potential. Or you can say the relationship between field and potential. So now dV is equal to minus E dot dr. I can find V by integrating. Integral of dV is minus integral of E dot dr. That is also there. Okay. Yes, so this is the relationship between electric field and electric potential. So what does the negative sign mean? It means how potential electric field is always flowing from higher potential to lower potential. And what is this term? Potential gradient. Okay. So the question could be, show that electric field is the negative gradient of potential. Show that electric field is the negative of potential gradient. That could also be a question. All right. That could also be a question of this derivation in your PU. Okay. So students, what is potential gradient? So if you have electric fields like this, okay. Okay. And here you have 3 equipotential surface. The next equipotential surface is here. The next one is here. So here what happens? V is same. But here V is changing. Okay, voltage is changing. So that the rate at which potential changes with respect to distance is called potential gradient. Do you understand that? Yes. So I think that much concept is enough for today. Okay. There is a question here. These are all simple questions. The solutions are also here. You can just go through the question. We will do this question. If the electric potential in a region is given by Vx is equal to 10 log x. Okay. If it's given by Vx is equal to 10 log x. Okay. Find out Ex. So we know that electric field is the negative gradient of potential. So minus dV by dx. Now this will be equal to differentiating. Log x is 1 by x. So 10 into differential of log x will be 1 by x. Sorry. 10 into 1 by x. So 10 into 1 by x. So E is going to be equal to minus 10 by x. So that is the electric field, which is going to be equal to minus of 10 by x. Hi, Ramesh, Kavya. Okay. Yes. And there is one more question here. I think I should do that also. You're making me feel bad. Let me do that also. So the electric field in a region is given by Ex is equal to what? Minus 2x square I cap Newton per coulomb. Okay. So the electric field is given by minus 2x square I cap Newton per coulomb. Now the electric potential is given as V0 is equal to 20 volts. Okay. Now find the expression for V of X. How will I find V of X? So first thing, I have to find E, which is minus dV by dx. So when I differentiate, minus 2x square will become, dV by dx will be minus 2x square. Minus minus will become plus. Okay, plus 2x square. So from this, Vx will be what? In differential of this, so 2x cube by 3 plus constant. Integral. Whenever you integrate, you put a constant as well. Okay. Whenever you integrate, you put a constant as well. So this is your V of X. Now how will I find V of 0? V of 0 is by substituting. So 2 into 0 cube by 3, which is what? 2 into 0 is 0 by 3 is nothing else but 20. So you will get this is 0. So the constant will be 20 volts. Okay? Constant will be 20 volts. Now I have to find the potential difference, V2 minus V1. Okay. So now I have my total Vx is what? I already know it's 2x cube by 3, but I know the constant also now. So it's plus 20. So to find V2, to find V of 2, I have to do 2 into 2 cube by 3 plus 20. So 2 into 2 cube is 16. 16 by 3 plus 20, which is 76 by 3. You do the math, you'll get the answer. Now V of 1. V of 1 will be 2 into 1 cube by 3 plus 20. Okay. So this will become 62 by 3. You do the math, you get the answer. Now to find V2 minus V1, you just subtract the 2. You will get 4.67 volts. Okay. So you found out Vx, you found out V2 minus V1. How did you find out Vx? Did you all understand that? Very easy. You just had to do the E is given. E is how much? Plus 2x square. So this is the same as dV by dx. dV by dx you differentiate. It becomes 2x cube by 3 plus c. Now we know one value of x, which is 20. So you substitute the value of 20 and you get the value of c. Okay, that's all. Alright, so these are some problems based on potential gradient. Okay, students, I believe this class has been really helpful for all of you because we've discussed each portion and problems based on that. So after this class, you should be very thorough about all the topics. Yes? No? So all those who are watching after the live, please let me know in the comments how the class was because I would love to hear from you. Okay? Because your feedback and your comment keeps us going. Okay. So please like the video and let me know in the comments on how the class was. Students, if you're looking for offline classes for anything, let it be JE, NEET, or even if you're an 8th standard student and you're looking for good foundation, like very strong foundation, we have got you covered. Okay. We have an offline center right in Bangalore at JP Nagar, 822 3rd floor, 24th main, second phase. Okay. So you can take a screenshot of this and you can go to the center, book an appointment. Okay. So under the video, there's a description, right? In the description, there's a Google form where you can book your appointment. So if you book your appointment and go, the best part is all the teachers and people will be there to guide you and clear your doubts, and you can talk about your future. They can guide you. All sorts of things. Okay. Now, if you're confused, like, should I join or not? Don't sit at home and think. Go to the offline center, visit the offline center, talk to the faculties, talk to the students there, and then you can take a call. Okay. So please do visit the JP Nagar office. Now, if you're not in Karnataka and you want to go to offline classes, we have other locations as well. So in the Google form, you will see all our locations, right? So the advantage of going to offline class is that, you get personal mentorship. So right now I teach, some of your chats I can see, but I really can't, see you and check if you're listening and all that. But if it's offline, then what is the advantage is that, people interact, you are monitored. So you are under pressure, not like that pressure, but there is someone to monitor you. So you will do well. Okay. So I always prefer offline centers, and we are here to give you free classes online. So offline will be more helpful for you. So please do try to check it out. It's all your decision. So as a teacher, I want you to tell you, please do check out our offline centers. Okay. Azrush, you will join if I am the offline teacher. See, you have better teachers than me in offline. Go visit the center once, then you will get to know how good our teachers are. Okay. Yes. Okay. So students, please send this class link to all your friends. Tell them to join. Okay. Yes. So I'll see you with another class next week. Okay. Bye bye. Take care. Eat well. Sleep well.